We've been asked to get started, so I know people probably still wandering in from lunch. So welcome to the Grand Challenge 2 session. I'm Dominic Boccelli. I'm a professor and department head of civil and architectural engineering. Starting with the intro with me also today is going to be Courtney Crosson. She's assistant professor in architecture, School of Architecture. So we're going to do just a quick introduction just to get everybody on board about kind of what we're doing with the session, and then we'll start with our talks. And this thing over here. All right, so just, I know I got talked about this morning, but I'll talk about it again. So as part of the strategic plan, this is part of the strategic plan, building a changing world. This group has hosted 2 different workshops. It was open to the faculty. One was done in May and one was done in October. The objective of the workshops were to identify existing areas, strengths, and interests here at the University of Arizona, to trying to take a bottom-up approach to where efforts would be going. These interests have been organized into the focus areas of RESTRUCT. So the 4 different areas that we've had today going on in this symposium, that's coming from based on the faculty interests and research. They've also provided seed grant funding to support some of the research activities. Courtney and I are both in a group that have received some of that funding, so we'll be talking a little bit about that in the intro and throughout this talk, or things are related. As far as create resilient and efficient urban and rural infrastructure, we've identified grand challenges for each of these focus areas from those workshops. And again, based on the faculty interests. So I just want to say kind of clearly, because I know at least in engineering, people tend to go towards NAE grand challenge when you say grand challenges. These things intersect with grand challenges, not only NAE, but other organizations as well. But again, they're really focused on where our faculty interests lie and what are the big problems that they're bringing to bear here at the U of A. So building on strength. So the overarching theme of this particular focus area is the redesign or design of the built environment for a resilient future. So, and this is broadly speaking, emphasizing adaptation strategies to mitigate long-term forcing factors, things like climate change or limited resources, and improve livability. So that's a really broad description, and that should be considered to be broad. And a little bit more specific under there are 3 different areas: so decarbonization, dematerialization, circular metabolisms, basically ways of reducing or reusing what would traditionally be a waste stream, creating efficient urban food systems, so bringing food to the population and doing so in an efficient manner with respect to resources. And then last one, integrated water resources management over multiple scales. So thinking about how do we do water resources management, basically from the source to the tap, and basically reusing that again, reclaiming that water. So these can all kind of be tied into this idea of achieving a net zero resource consumption in the built environment. So net zero may not always be feasible, but it's a goal that we can strive to. And if nothing else, we're improving our efficiency. So these all kind of fit into that idea of a net zero resource consumption model. And what we're going to be talking about today, we have a talk on efficient urban food systems, integrated water resources management, and that they tie into this net zero resource consumption. And one of the seed grant fundings that we got was on net zero urban water. And Courtney is going to talk a little bit about that, just to give you a brief idea. So we kind of we used water today as the theme, but when we talk about net zero resources, it can be much more. It doesn't have to be water, right? It can be any kinds of resources. And the other thing we try to do is bring some of the talks together that go from both the technical side all the way to the policy side, because we're never going to do all of this unless we start to incorporate all of that, all of those different aspects together in a solution.
Thanks, Dominic. So like Dominic said, he and I are part of a group that received some seed funding from the Building Changing World initiative. And we've been working with colleagues also in hydrology, policy, geography, as well as architecture and engineering. And so our focus has been on this question of achieving net zero urban water. And so you can see our 2 main specific aims up here, and then a few other specific aims below those. But basically the aim is to come up with, both as a tool and an outcome, an integrated net zero urban water model. And then from that, adaptive designs for integrated water infrastructure and management. And we've been meeting this semester every other week and then have held 2 workshops to date. And so to start out with, for our first workshop, we had this diagram as a basis of discussion. And so you see the white is basically the urban water system. And then the harder lines are basically the pipes, and then some of the natural systems are also represented, the built-in natural systems. And then overlaid with that, we had discussions with our colleagues in social sciences, and overlaid, these are some examples of the social systems that overlay this built-in natural environment, but you can start to see how these overlap and interact. And then lastly, what we've done this semester is come up with 5 specific research areas within this larger net zero urban water framework initiative. And today our 4 talks will not map directly into these 5 research areas, but follow them fairly closely. The first one looking at urban agriculture, and then the second one really Dominic's looking at this second research area about retrofitting the urban water system for decentralized and alternative water sources. My talk is third, and I'll be looking at both green infrastructure in the research area 3 and then also 2. And then Adriana will finish us off with looking at public preference and current engagement, and then also looking at green infrastructure within that too. So without further ado, we'll turn it over to our first presenter.
So first I'll just say what we're going to do is we'll have
Yes, thank you, Tom. I'm Joel Cuello. I'm a professor of biosystems engineering here at the U of A. So anyway, I am in the habit of, because I would like to remind my students often that we together in the 21st century, meaning we scientists and engineers and social scientists and economists and entrepreneurs and investors, we together are well privileged to be occupying the commanding heights for designing the innovative solutions for the planet's most pressing and most impactful grand challenges. And today we have a number of these grand challenges in part because of our planet's burgeoning population. Today, as you know, our population is now at about 7.5 billion. By the middle of the century, that's going to go up to about 9.7 billion. So that's like adding another China, another India to our planet in terms of population. And there's also this dramatic demographic shift from the rural areas into the urban areas, so that by the middle of the century, over 70% of us will be living in urban areas by the middle of the century. And that's despite the fact that cities only occupy about 4 to 5% of the land surface of the planet. So in fact, 3 years ago, there's only about 440 cities worldwide with a population of between 1 to 5 million each. And in a matter of 10 years, in 2030, that number is going to go up to 560 cities. 3 years ago, there's only 31 cities with population of at least 10 million. And in 10 years' time, that number is going to go up to 41. So it's not only that for sure we're going to need more food going forward, but that a lot of this food will have to be distributed in cities that are scattered worldwide. So how much food exactly do we need? Well, the United Nations projection is that we need to increase our food production by 70% by 2050 to meet the demand. And in terms of crop production, we have to double it actually. So, but this is a tall order because already food production is consuming 70% of all freshwater withdrawals worldwide. Agriculture is also pretty much using up almost half of the land area of the planet. And in terms of energy expenditure, food production and the supply chain is expending 30% of the global energy consumption or demand. So the crucial question now is, do we have all of these critical input resources to be able to meet the demand of our planet for food? And as if that's not enough, our increasingly erratic and changing climate is also introducing a lot of uncertainties and disruption in our global food production and supply. And so all these lead to this inescapable thought that, at least in terms of food and the input resources that are needed to produce the food, such as water, we all are living in a world of scarcity. But then again, I'm in the habit of reminding my students that we are occupying that commanding height of creating these innovative solutions to address the grand challenges of the planet. So we only treat this world of scarcity as a mirage, and that is as a beguilingly deceptive, but by no means permanent condition. So to put this in context, we need to consider other worlds that are really worlds of scarcity, such as Mars. So on Mars, there's no arable land, there's no running water. It suffers from wild swings of extreme temperatures, and it's also constantly bombarded by deadly ionizing radiation. So bottom line, there's nothing that grows on the surface of Mars, at least outside a built environment. But inside a built environment, you can grow pretty much anything on Mars. And this is no science fiction. I did my postdoctoral fellowship at NASA Kennedy Space Center in Cape Canaveral in a division called Controlled Ecological Life Support Systems. That's a fancy name for space farming. So that was me much younger. So this is a biomass production chamber. It is sealed. And in there, you control the important variables for growing crops: temperature, light, meaning light intensity, light quality, light duration, the relative humidity, the air movement, the nutrient composition in the hydroponic nutrient solution that's used. And what NASA has shown is that it can grow pretty much all types of food in this sealed type of environment for long duration space missions. And when I moved here to the University of Arizona back in 1995, I continued my work on controlled ecological life support systems, including designing the very first hybrid solar and electric lighting systems applied to bioregenerative space life support systems. And we did some simulations for some landing sites on Mars, and we've shown that by the use of these controlled environment systems, we're able to reduce the energy demand for food production in space by about 40%. And of course, decades have passed, and I'm sure that the efficiencies of fiber optics are much better now, and so you can arrive at much greater reduction in energy demand. So what NASA has shown is that when you have technology and innovation, which is a technosphere, appropriately applied to our resource sphere, which is our world of scarcity, it is well possible to transform our world of scarcity into a world of abundance. So back on Earth, in Japan, in the 1980s, a number of entrepreneurs essentially employed or applied the innovations that NASA has developed for extraterrestrial life support systems to develop these closed, controlled environment plant factories or vertical farms. So that was the beginning of the vertical farming industry on Earth, on our planet. And it's particularly interesting for Japan because Japan is well known that it doesn't have a lot of land resources to feed its large population. So it really made sense for them. And again, as I said, this is no science fiction. This is a vertical farm that's commercially operating in Japan. There's a number of them. This is called Mirai. And you see the shelves upon shelves of crops that are grown without any soil, using hydroponic nutrient solution. There's no sunlight. They're using LEDs of different light qualities. They're controlling the temperature, the relative humidity, the airspeed, and so on and so forth. So what you have here is maximum yield, maximum quality, anytime, anywhere, basically. This is another vertical farm spread in Tokyo. This is right here in the United States, in New Jersey. It's called Aero Farms. Another one in the United States, in New York. It's called Bowery Farm. This is in Silicon Valley. It's called Plenty. Another one in Silicon Valley called A Essence Grows. So there's a number of these that are now in operation, not only in the United States, but also in Europe, even in China and India. And this one is in China. I was just there last year, and they brought me to visit this particular vertical farm. And it's now commercialized. So the gentleman to my right, that is Professor Toyoki Kozai. He's been a big exponent of vertical farming in Japan. And in fact, he was a past president of the Plant Factory Association in Japan. and he's a big exponent for the warehouse type or warehouse paradigm for vertical farming. Dixon DePalmier is a retired professor at Columbia, and he wrote a book called Vertical Farming, and he's the big exponent for the high-rise type or paradigm for vertical farming. What I've been championing is the modular structure for vertical farm, just because it's more accessible, more affordable to more people, and so it would allow more people to gain entry into the vertical farming industry. So specifically, I'm championing the minimally structured, modular, and prefabricated vertical farm, which could have versatile configuration. You've got your modules can be arranged in different geometric configuration, like a cylinder configuration, a linear configuration, and of course, there are many other possibilities. And of course, a practical example of a vertical farming module would be your standard shipping container. And in fact, a number of companies have been working on retrofitting shipping containers, turning them into modular vertical farming units. Here at the U of A, we have one that we play with together with my grad students. We call it the Arizona Green Box, and it's been funded by the UA Green Fund. But we also design our own original growing systems inside the modular unit so that we could really maximize the amount of crops that are being produced. So this is called the V-Hive Green Box vertical farming unit. It's patented by the U of A. And this is another one. This is a mobile type of vertical farm. So it constitutes really a whole new paradigm for vertical farming. As opposed to a fixed vertical farm, you now have a mobile vertical farm with those mover robots. Kind of remind you of that system that Amazon has in its warehouses. So anyway, vertical farming is really emerging and spreading worldwide today. But it's not only because it leads to maximum yield, maximum quality, maximum flavor profile, maximum or optimized nutrient profile for the crops that they produce, but also because they save on the input resources that are needed to produce crops. For instance, it saves on about 80 to 95% of water compared with open field cultivation. And now with the application of data analytics as well as artificial intelligence, there's now ways as well by which you could really minimize the input resources such as heat, nutrients, nitrogen, potassium, phosphorus, CO2, light, and so on and so forth, so that you can still produce the same amount of yield and the same quality for the crops. And of course, it's not only conventional food crops that you can grow in vertical farms. You can grow algae, which produces a lot of valuable chemicals or products. You can produce fish, and you can produce mushrooms as well. So then how do we make vertical farms as integrated components or nodes in a circular economy in an urban area and ensure its sustainability and resilience? Of course, it's good if cities have access to renewable forms of energy such as solar energy and wind energy, but not all cities do. However, there's one thing that you can rely on with cities, particularly big cities, and that is they produce tons of waste. So let's consider New York City. And I'm citing New York City because there's a number of vertical farms now in New York City. So New York City produces 1.3 billion gallons of wastewater per day and 38,000 tons of solid waste per day. And this is a map of New York City showing the geographical distribution of the 14 wastewater treatment plants that's operating in the city. And I highlighted this one. This one is the Newtown Creek Wastewater Treatment Plant, which is on the Brooklyn waterfront on the East River of Manhattan. And this is what it looks like. It's famous for these eggs. So these are really digester chamber. They are still laden digester chamber for performing anaerobic digestion. So that's been designed to accommodate 1.5 million gallons of sludge daily, even though they're not really operating at full capacity yet, and up to 500 tons of organic food waste per day. So what's remarkable about this Newtown Creek wastewater treatment facility is that they're not only using wastewater, they're collecting organic waste, such as food scraps from hospitals, from schools, from homes, offices, and they're adding them into the sludge. And the great thing about that is with wastewater and organic waste as input, you produce not only treated water, but renewable natural gas. Of course, it's biogas with methane, but with further processing, you then generate pipe-ready renewable natural gas, as well, of course, concentrated fertilizers. So based on this, it's possible then to construct this circular economy scheme where you have these nodes of production and consumption that are interlinked by the influent and effluent streams that they produce, so that overall you really minimize and hope you can reduce to zero the waste that is produced by any one of these nodes. So this is very much consistent with the aspiration here to come up with a net zero resource plan. So for instance, the homes, they produce wastewater and food waste. They go into the treatment facility, and there's treated water and renewable natural gas that can be channeled back into the homes. The vertical farms, they produce a lot of inedible waste biomass. They could be brought into the treatment plant, and in return, you get water, fertilizer, or renewable natural gas. And of course, with vertical farms, you produce local, fresh food. You cut down on carbon emissions because your food doesn't have to be transported thousands of miles from the West Coast to the East Coast, in this case, for instance. So this is the grand plan that Dominic shared earlier, and I kind of just want to emphasize the urban food production here. But one way of looking at this as well going forward, perhaps in the future, is that you can consider this entire thing as one plane. And I could refer to that as the water plane. And then you've got the food plane, and you've got the energy plane. And each one of these planes are interacting with one another. So you have your net zero urban water within the context of water, food, and energy nexus. So I'm proposing that the net zero urban water is most effectively designed within the context of a water, food, energy nexus. So that's the food for thought that I'm sharing with you today. Thank you. Oh, do we have a few minutes? All right, we got a couple of minutes, I suppose. I'm happy to answer any questions you may have. Yes, please. Yes, as I mentioned, it's not only conventional food crops that can be grown in vertical farms. You can grow fish. So you can grow pure aquaculture, or you can link hydroponics and aquaculture so you can have an aquaponic system. And as I mentioned, you can grow algae as well. Algae produces nutraceuticals, pharmaceuticals, even cosmetic ingredients, and food products as well. And mushroom, which has a gazillion applications. Right. How quickly? So I would say in the next 5 years to 10 years. I'll give it a decade. Because really, the rate of development in the last 5 years has been phenomenal worldwide. And now there's a lot of investors that have been investing in here, within the ag tech sector of investment. A lot of it has now been going into vertical farming. So it's now really gaining a lot of mainstream acknowledgement and recognition. And I think that it's just going to accelerate at a fast rate. Yes, Henry. Right. In terms of policy, well, one thing that I have in mind actually is the use of treated water for food production. That is a sensitive matter. I think in the United States right now that's not allowed, but in certain countries that is allowed. And so maybe that's one thing, one area. The other one is, I guess, facilitation of the building of vertical farms in urban areas, because urban areas are notoriously expensive. And so perhaps certain areas could be designated for agricultural application. This is particularly true in Singapore. Singapore, as you know, is a city-state. It's a very small country with very limited land area. And so the government has designated a small portion of the land meant for agriculture. And now they're no longer interested in open field cultivation. They really encourage their people or the farmers to do vertical farming because it's a far more efficient, method of food production in terms of land area because you can go upwards, as well as in terms of resource utilization. Yes. Correct, yes. That's an excellent question. As I mentioned, the vertical farming industry began in Japan. And in Japan, it's very much readily accepted by the citizenry because the Japanese consumers, they're willing to pay for something that's really of high quality. I've been to, I think it's called Shinjuku, one area in Japan, and they're selling apples for $100 each because it appears perfect, I mean, in their eyes. So in Japan, this is true. They have no problem. In China, I was surprised because in China, vertical farming is really taking root. And that's because the population has been rocked by a lot of food scandals and food contamination issues. And so the families now are really concerned about the safety of their produce and the quality. And they're willing to pay higher premium for produce that is coming from vertical farms as opposed to open farms. And the same is true here in the United States. At least that's the public perception, as well as in Western Europe as well.
That's fantastic. All right, so I'm going to be your second speaker today. As I mentioned before, I'm Dominic Boccelli. I'm a professor and the department head in civil and architectural engineering. I'm going to be talking about real-time modeling and a decision support framework for drinking water distribution systems. And I want to acknowledge this is something we've been doing for probably 6 years now. So this is going to be really an overview of things, but I just want to recognize my current and former PhD students who are all from the University of Cincinnati, because I've only been here for a year and a half. And these are the students who, Masood and Paulo, are still working on this project. And I've got some students here who will be picking up, but they haven't continued it now. So we started off, Courtney started off the talk by bringing up this notion of net zero urban water. So this idea of going from supplies to the consumer and basically reclaiming it, reusing that water to try and minimize our new sources. These integrated water systems really require us to have both long and short-term decisions. So I tend to generally think about it, design decisions are generally thought of as long-term, long time duration decisions. When you build infrastructure, you're thinking 40, 50 years down the road. Operational issues are generally the short-term decisions, which you need to make sure these systems all work efficiently together. So both of these decisions have to be made within their specific systems and across the systems. And it's across the systems where we start to have some challenges. And the thing that I'm going to focus on today are really on the operational side of things, focusing on drinking water distribution systems. So while we have operational challenges with these integrated systems, they really, across the boundaries, both within decisions and across decisions, have similar challenges. And this is really just a short list, right? So we have limited or missing data, which we focus on, which we run into a fair amount. So I'm showing actually a little plot here of just where we had some data that we pulled out and missed and ways to try and fill data to give us some more information about a system. We need to be able to estimate unobserved system states, so why we'd like to know, for example, where the flows are everywhere in a system or river flows or things like that. We can't measure everything. We have to be estimating somewhere these states, and we need to be able to forecast those performance, particularly as we're making decisions. And incorporating that decision making, we have to include, at least my opinion, is we need to incorporate the uncertainties. There's all sorts of uncertainties that need to be incorporated to make sure we have robust decision making. And a lot of this requires operator input. Operators correctly aren't going to just buy into what a computer model tells them to do. So this kind of decision framework needs to be usable, but also basically giving operators information that they can incorporate the unmodeled aspects if necessary. So again, I'm going to be focusing on drinking water distribution systems as the example. That's what we've been doing, but we're looking at expanding this to a larger framework. So since probably not everyone is familiar with drinking water distribution systems, so these models, so this is an actual model here from a utility in Florida. They're meant to represent an entire system. They're not generally tightly connected to the data that utilities collect, meaning that utilities collect data and they see it, and then they have their model on another side. And in general, the model and the data streams aren't integrated. These models also are generally not adequately calibrated. I shouldn't say generally not, but they may not be adequately calibrated. They're tuned for certain times of a day or a season. Data availability is generally limited. So you can see this system here, which is a medium-sized city. It's only got about 15 measurements in the system between flows and pressure. So there's limited data, and the demand, how we use water, is really what drives how water moves through the system. While we have an idea of total demands, we don't necessarily know what that spatial distribution is. So we generally don't have the data at really small scale or individual meter connections. Now that is changing with smart meters. More utilities are collecting that data. A lot of the ones that collect it have actually no idea what to do with it when they collect it. And that's what we're hoping to take advantage of. But in the meantime, a lot of utilities haven't gotten to that point yet. So we generally need to be able to estimate this kind of the demands throughout an urban environment and then forecast it, which will allow us to make our decisions. So very broadly, so we've developed an algorithm. My student Jin-Duan Chen is fantastic. He developed this composite demand hydraulic model. So what he did is he basically took time series modeling techniques to represent demands, because if you look at how water is used in an urban environment, it's very diurnal. Right? It goes up in the morning and down towards lunch, and then back up again in the evening, and then drops down overnight. So very conducive for using time series modeling. And we've linked that with a hydraulic solver, something called EPANet. So basically, if we know the demands, we can know the flows and the pressures throughout the entire system. So the algorithm we developed now is able to estimate consumer demands at an hourly time step or sub-hourly if we wanted to. And we have using that data, we can estimate parameters of our time series model. And that becomes important because that really allows us to forecast. So we're the first group to really start thinking about how do you take this data and just trying to say, how do we estimate the demands, which a lot of people did, but how do we use that information to do forecasting, which allows us to do decision making. So we've done this assessment with a real world system. So that's what I'm showing you here, this system from Florida. Has 6 flow measurements, 9 pressure measurements, and this has 60,000 service connections. And the model has 12,000 nodes. So a service connection is basically any meter. So this is as far as these kinds of models goes, this is pretty detailed. A lot of models don't get down to this level. And most of this area also is residential. There's a couple small commercial zones, but it's mostly residential. And we're using this as our test case. We did a lot of field work down in this particular area of Florida. So the biggest challenge we have is we got to reduce the number of unknowns. So with the pressure data doesn't really help much with estimating demands. So we basically have 6 flow measurements and 12,000 unknowns. So that's not a feasible problem. So to reduce the parameterization, we've been doing work on different clustering techniques. This one was done with using sensitivity information. So how did the demands affect the flow values that we have measurements for, using a singular value decomposition approach. And that gave us these 4 clusters here. So the northern region gets split up into 3 zones. The south region, just 1 zone. The northern region is more densely populated. And what we've done is we've estimating the demands in each of these clusters. And then we have a time series model that we can use to forecast the aggregate demands in those clusters. So we've got 4 clusters. This work is showing you 4 clusters and 6 different for the 6 flow meters. And the flow meters here are given by the arrows. So I'll start here. This is the treatment plant. There were 2 flow meters out of the treatment plant. There was 2 in this northern region. Where the flow branched off, and then 2 in the southern region along 2 parallel paths. So there's lots of results I could show you, but I'm going to focus on just the flow measurements. So this top row here are the 2 flow meters leaving the treatment plant, and we have pretty good, the black lines represent the estimated values and the blue are observed. We get pretty good representation of these values, which is nice because we're not saying what the total demand is, but we're coming back and we're saying, okay, well, we're getting basically the total demand, so we know the demands are giving us the total overall system demands. This middle row here are the 2 flow meters in the south region. So the one in the east we tend to overestimate, and in the west we underestimate, but mostly because this is in one big cluster. So if we had a little bit more data, we could maybe split this and get better spatial distribution of our demands and do better there. But all in all, that's still not bad. And oops, and then these 2 flow meters, we get almost perfect results because each flow meter basically ends up being associated with a cluster. So these are all improvements to what the utility had originally with their network model when we just ran it. So, and I try to tell my students, that's great, we can match those 6 data points, but what does that really mean for the overall network? So we also did some tracer tests, which I absolutely can't go into in this. 40 different monitoring locations, and we compared the tracer signals before and after we did this work. We see an improvement overall in the system in the transport. So we know that we're doing a better job representing the overall dynamics within that system. And what that allows us to do then, if we feel like we have a better job of knowing what's going on in the system, we can start to do this in real time. We can do real-time demand estimation, forecasting, and that allows us to do some operational decision making. So where we're at right now, and I'm going to go into that decision making part, we're talking about energy. So drinking water distribution systems generally use about 13% of the US electricity. Pump scheduling is normally done modus operandi. So you've got your utility operators there in a command center. They utilize a knowledge about future demands. So this represents kind of a diurnal pattern, a discretized diurnal pattern that generally happens every day, different magnitudes, but that's pretty much the shape. They know the system, and they usually know it really well. They know at least where the water is going, roughly. And they provide manual control, which tends to be conservative, which is okay because utility operators want to make sure we have water. It can be suboptimal. They're not trying to always say, okay, well, hey, we've got this quick cost break here. Let's go and pump more right now. They may not get that information enough time. And they may not be robust. Those decisions might not be robust against unknown events. So we've taken the approach, this demand estimation and forecasting algorithm we've developed, applied it to the real world. Now what I'm showing you here, really we just want to, so these are 2 different clusters. The black lines represent estimated values. These blue bars are actually a 1-hour head forecast. I'm not going to get into details on that. But what's important is we can stop at this time and say, okay, this is our real time where we're at now. We can forecast demands ahead in time, as well as the uncertainty, and that provides us the basis for our decision support. Because if we can say, well, these are our forecasted demands, we can simulate that in our whole network model. We can look at, for example, this is a tank level. So this red line represents an expected value, and all these little blue wispy lines in here represent the uncertainty or the response to uncertainty in those demand forecasts. So when we try and make pump decisions, we want to make sure that we're accounting for all that uncertainty in the system. And so we're using this information now to try and improve pump operations while accounting for that uncertainty. And how do we do that? So we're using a model predictive control, and I'm not going to get into the details of it, but if you say, okay, right now, time TI. So right now, I'm going to forecast these demands, and this is basically what that looks like, this Monte Carlo simulation. This is the tank response to it. So I know my forecast over some time horizon, let's say a day. We use an approach called the DREAM algorithm. It's a Markov chain Monte Carlo type approach. And what we do is we determine the time duration between pumps going on or off. And we're trying to do this to minimize costs and maintain tank levels. And this is schematically showing what you're doing. So if the pump starts off at on, we're trying to estimate, okay, how long till you turn it off? How long till it goes back on? How long till it's off? How long till it's on? It's a continuous formulation. Other people have tried to solve this with as a binary problem. This is a bit more easy to solve. And what we do is even though we're making a solution for this 24-hour time period or this longer period, well, we're going to use that solution for just a short time step, delta t, maybe 15 minutes, maybe an hour. You run in that solution. Then what you do is you collect additional information. You get to that point, you collect the additional information, you update the decisions. So what it's giving us is a rolling time horizon of decisions that are continually updating as we're getting more information in the system. So we don't have to rely on our forecasts. So a lot of pump optimization that's been done in this area has been very much deterministic and sets a case for 24 hours and then leaves it. So just to give you a rough idea of what this looks like. So this is a plot of the pumps, different flows. So this is if you're saying, okay, I'm at 7 a.m. This is my pumping schedule for the next 24 hours. So this is we're just at this point. So all the pumps should be off. Here you see they're on for a little bit, then they go back off and they come back on. This point here is actually where the energy costs are lower, so we really want to do more pumping here. So you see that a little bit. But the other thing is these are 2 tanks that were in the model. You see the tanks are slowly draining. So at the end of 24 hours, they're getting low. Because all we're doing right now, we're saying, here we are at 7 a.m., what's the best way to operate the system? All we really care about is saying, hey, these pumps should probably be left off. 8 a.m., we're going to go collect more data and determine what the pump should look like. So if we take that, and now let's say we're at the end of 24 hours, we're looking back as to what we've got. So this is what the actual solution would have looked like. Here you can still see some pumping on in the more expensive time period, but then you see all the pumps are on when the rates are cheaper. The tank levels you can see for both of them are coming back up, which we want. We want the tanks to be full. And you can see here that this tank never even gets close to its minimum value. It's not really empty, but this would be its minimum value. And that's because of the uncertainty. You'll see that in a minute. This tank, it's allowed to get pretty close to, it's not really going to be empty, but it's a minimum value that utilities would be comfortable with. And then it comes back up again. So this rolling horizon, even though initially we say, yep, it's going to drain with this solution, because it's always forecasting and it doesn't want those tanks to empty, it brings the tank levels back up. And I just want to show you this. So this is kind of a graphic of what is really be going on. So this big gray bar represents, this is where you're at. This particular time, the red bar is the forecasts. Those dash bars are basically your past expected, or your red bar is your expected forecast. The dash bar is what you had in a previous time. It starts to fade away. And those little blue wisps, again, are the uncertainty associated with it. So you'll see in this first tank, there's some really large uncertainties here, which is why it never gets close to the minimum. This tank, the uncertainties were much less in it, which is why the tank was allowed to get closer to its minimum value. So within the context of this net zero urban water, long-term, this integrated water resource management, it's going to require coordinated operational decisions. There's going to be multiple challenges associated with data availability, model calibration, state estimation, uncertainties, getting models to talk to each other. But what I've tried to do today is present an approach that integrates a real-time demand estimation or an estimation approach, which could be extended to other areas, and forecasting with a rolling time horizon decision support for pump operation. So we've been approached with, so we've been approached by like the Army Corps for doing some of this for the reservoir management. When I was still in Cincinnati, our storm and wastewater group was very much interested in how they could use this kind of technique. And I just want to acknowledge the funding we've had from that. And so that's a very quick summary of our project of trying to look at making decisions in real time, incorporating information and uncertainty, and improving basically, in this case, the energy utilization from water utilities. I'm happy to take a couple of questions. Yeah. Yeah, so the actual solution, what it does, the algorithm we picked actually will provide multiple solutions that are similar and would allow utilities to see, like if you took 10 solutions, say, oh, all these pumps should be off, it helps them to say, yeah, they should all be off, or should they be on, or if there's a question, they could use some of their own engineering judgment, but the algorithm will try and work and keep the pumps running when the energy costs are lower. And you could also start to integrate this, incorporate that with energy costs. As energy costs change dynamically, you could also integrate that and have the energy costs change, or even incorporate uncertainties in what you might think in that energy forecasts, so to try and come up with better solutions. Change the behavior. Could you in this case? This case is probably a little too aggregate, but as we're getting to the point with the smart meters, you certainly can start to do. I know some colleagues in Europe where they have some of the smart metering has been a little more commonplace. They've looked at how do you get data back to the user on like their cell phones and try and encourage them to use less water. So there is some of that that's starting. Oh yeah, this is definitely a generic approach. Yeah, yep. I mean, there's some setup that has to be done, but yeah, you could apply it to different cities. In this particular model, the one thing we're looking to incorporate from an aging perspective is just as the pipes change, the energy losses in there change. If you get enough data, this can start to be used for leak detection. I have a postdoc right now who's looking at how we could use this, start using it for utilities right now. The data they do collect more for burst detection, like big leaks, a big pipe break, detecting them fairly quickly. To get down to smaller leaks, you'd have to have a little bit more resolution in the spatial data. But certainly that's actually where utilities have been the most interested in this kind of approach right now, is on leak detection. Okay, well, I'm going to move on because I'm sure I'm out of my time. So, thank you very much. All right.
Yeah, and I think just yeah. Great. Those were two really excellent presentations. So I will be talking about retrofitting cities to achieve net zero urban water, and particularly with decentralized infrastructure. So I'm an architect, and so I'm interested in designing and implementing adaptive solutions. And particularly I'm interested in these decentralized solutions and the network impacts of those solutions. So within the net zero urban water diagram that we introduced, and of course it's now missing our new green area that I really like that Joel added. But I'll be particularly addressing number 2 and number 3. Okay, so I start out with this fact because like Dominic was just answering, we do have aging infrastructure, and we have a lot of deferred maintenance, and we have a lot of future expansion in our urban water system. And so the question really is whether or not we're going to put that money towards continuing to invest solely in our centralized system, or if we might use some of that funding to add decentralized solutions and add resilience to our urban network that might be more agile at addressing some of our population growth issues and climate change issues. Okay, so this talk is going to look particularly at 2 different areas of incorporating decentralized infrastructure. First, part 1 is infrastructural innovation, and then the second part is looking at regulatory innovation. And underneath those 2, I'll talk first very briefly about a research project, and then the second part is bridging that research project into some of the work that I'm doing with the city and the county, and also with Henry Johnston, who's here from GLHN Architects and Engineers. So in my work, I do both research, but then I also teach design studios that look at how we take that research and then start to speculate and envision new design solutions for our urban environments. Okay, so the first research project is looking at integrating decentralized rainwater harvesting. And it really started from this fact that I had heard thrown around Tucson quite often by the public. And it was, this is one example. So in 2016, our residential water demand was 87,000 acre feet, which equated to about 29,000 acre feet of imported water. In the same year, we got 125,000 acre feet of rainfall, right? So this is what I hear. So we get more rainfall than we actually use in Tucson. Isn't that crazy? And so, right, so that's the rainfall is equaling to about 144% of that residential demand, or 430% of our imported water. But of course, we know the situation is much more complicated than that. And so this shows you some simple maps. These are township squares in Tucson, which are 1 mile by 1 mile squares that we have data on for both the supply and the demand. So on the left is annual, and then on the right is the month of June. So we have context limitations, of course, right, with rainfall. We only get it in bursts in very specific times of the year. And then, of course, we also have infrastructure limitations. We only have a certain amount of catchment surfaces, and we only have certain storage volume sizes. So this project looked at, what would be the storage capacity necessary per township square, per household, to achieve net zero water in Tucson. And I worked with a physical geographer on this, using a few different types of remote sensing methods, and then inputting into water independence or a net zero urban water model using MATLAB. And so basically we solved for the fixed parameter being the roof sizes, and we used we isolated the different types of roofs and the slopes to accurately estimate the water collected. And then we solved for the necessary cistern size to reach a net zero urban water target. And you can see we had a few different scenarios. The one I'm going to show you was the most practical, which is where we only replaced imported water, basically CAP water, Central Arizona Project water. And then we also assumed a 30% conservation. And so really quickly, this is the 1 mile by 1 mile township square sections. And we used 10 years of real rainfall data from 2007 to 2016, interpolated to the nearest weather station. And those 10 years of daily rainfall data represented mega drought conditions where we had back-to-back-to-back drought conditions. And so basically, the results were, you can see that some areas for an average household, most areas would only need sort of a hot tub size storage, and then many other areas would need something more like 10,000 gallons to 15,000 gallons, which is about an average pool size. And so, that's a glimpse. Of course, that there's a lot more to go into with that project and the analysis that was done and in the findings. But what I want to connect it to is then work that I've been doing with the city and the county, particularly funded by Pima County Flood Control for the last 3 years. They've been funding a studio I teach every fall semester. And basically they provide the students with 6 different sites throughout Tucson, and we design decentralized solutions to those sites that mitigate flooding and then do other, realize other co-benefits for those different areas in Tucson. And so here's one example. I'll show you 2 very brief examples. But basically, this one is the technical drawings have been finished. So Tucson Department of Transportation is building this project on Camino Miramonte, if you know, near the Whole Foods on Speedway. But this is basically using passive rainwater harvesting through a inverted crown street to harvest rainwater, reduce flooding, and then add in pedestrian safety elements. And then this is another example that you may all be familiar with, is Elkhorn Mall has a lot of parking and is also termed the headwaters to a lot of downstream flooding, particularly in Palo Verde neighborhood. And so the city of Tucson's been successful at an ongoing negotiation that looks like it's going to be successful and finalized to purchase some of the back parking lot areas to put in a park and to execute a green belt actually around Elkhorn Mall. So those are 2 solutions there. So the second part is looking at regulatory innovation. And so this project came from more my experience in practice, and knowing that the technological innovation really does exist to realize at least net zero urban water or net zero buildings. And the frustrating part has really been this regulatory innovation side. And so this project looked at basically starting with taking 10 commercial net zero water case studies, locating similar systems, doing an Arizona code analysis, looking at both municipal, state, and federal code, across both the building code, but also public health and environmental code, and then reflecting that back into an actual net zero water building design. So I'm not going to dive into this, but this is to give you a general idea. These are 10 different projects that currently are in operation across the country that are net zero water, and this is rating the different issues they've had with code compliance in order to be operational, and the difficulties. This was outcomes from the Arizona code analysis, and basically all the yellow that you see on the screen are basically places that are barriers that need to change in order for us to have operational commercial scale net zero water buildings within Arizona. And then this is that third part that I was talking about, looking at a specific building design case study. And so really looking at 3 different systems, decentralized potable, then gray water reuse, and then third, on-site wastewater treatment, and the different code issues that exist across all those different regulatory environments that I mentioned. And so what you see is water touches all across the code. It's really complicated because it's definitely it's a main concern for public health, as well as environmental health, and then plumbing. And the vocabulary changes from one code set to another, and then a lot of these places of innovation are currently not even integrated really in the code where you would know where to begin as like an architect or an engineer trying to put in some of these more innovative systems. Oh no. Okay. Let's see. Well, I don't know what happened, but there's a couple more slides. So I'll tell you what they said, and then I'll finish up. Yeah, so basically, I looked at these two different areas, right, that I talked to you about, this infrastructural innovation that needs to happen, and then the regulatory innovation with that. And so in terms of in the architecture studio, how we've been looking at some of that regulatory innovation has been partnering with, last semester we looked at converting downtown Tucson into a net zero urban water area by 2050. And with that, we partnered with Tucson Water, Pima County Wastewater, and Pima County Flood Control, and partnered with different leaders in those agencies to, paired with the students, design new, basically prototypes where we could incrementally adapt and convert our urban environment over time. And we looked at that across 5 different water types: groundwater, rainwater, stormwater, gray water, and reclaimed wastewater. And so really figuring out, you might have heard this term, one water system. Dominic was talking about integrated water management, but really, how do we take all these different systems together and optimize for achieving something like net zero water? And with that, I will conclude. So are there any questions? Yeah. Mm-hmm. Mm-hmm. Yes, so the 2050 work, the city has been really collaborative. I think Henry can talk to that too. Every semester they send us people to work with us. So I think they're seeing it as definitely an idea generator. In terms of taking word for word what the students are producing and putting into policy, I think that direct link hasn't happened yet, but I think it's seeding a lot of important ideas. I think the other thing that the work does, and as a university I think that we can speak to in terms of municipalities, is we're a really important place, like almost like neutral ground, where I think all different departments can come together across the city and have these conversations and push ideas forward in a safer place than where they're really facing day-to-day, year-to-year decision making. So I think it's a really important ground for envisioning into the future and starting to figure out what we can do now. Like I said, incremental change, this idea of adaptive solutions. So hopefully that helps. They are, like I said, building projects from the other studio. So. Henry, did you have a question? Yeah. Uh-huh. Right. Correct. If every household did that in that square mile, they could achieve net zero urban water defined as simply replacing CAP water. Yeah, 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 yeah. Sure. Yeah, take that one home. Yeah. Yeah. Right. Uh-huh. Yeah. Yeah. Mm-hmm. Mm-hmm. Yeah. Yeah. It's a excellent and really important question. And so it's specific to rainwater. So I think that's, designing these systems holistically, I think is really important for that reason. So, if we just collect rainwater and then flush it down the toilet, yes, we are affecting our localized environment, right? We're taking rainwater away from it. But if we do actually design an integrated net zero urban water building, what would happen is you'd reuse that water on site. So maybe you take rainwater, put it into your shower. That shower water is collected and then used for irrigation. And so it does finally reach the outside environment. And if you look at definitions of net zero urban or net zero water, so the certified projects that I was showing you, that definition says that you have to use all the water on site for benefit and maintain hydrological conditions. So I think it's a really important caveat when we have these discussions. It's not just a kind of an engineering solution. We have to think about our natural and social systems and how we're affecting those long term. I also think that's why we're so interested in this idea of net zero water across all these different disciplines, because like you said, there's all these interlinked effects. And so looking at an integrated model, we can start tuning this whole different, it's a whole portfolio of solutions. There's no silver bullet, I think, to the Southwest scarcity questions. So thanks. That's good. Oh, you have one more? Yeah. Sure. Yeah, and I think this is where Dominic's work's really important, and specifically getting those almost fixture level use data to successfully model those reuse questions. And even down to conveyance of biosolids or whatever you want to call them, through our wastewater. I know that there's a lot of, like even in the studio last semester, Pima County wastewater said, oh, maybe don't use too much gray water. We need water to convey the biosolids, where that was something that Tucson Water was promoting more. So it's really fine tuning the model to figure out, yeah, like we've been talking about, like what are the consequences, and it's all interlinked. Yeah.
We also talked about not in this project, with another project we did with the utility out in Nevada. They ended up with a lot of water quality, with disinfectant byproduct regulation issues because they were using less. They had overbuilt, then they had water conservation, and before they know it, they started ending up with water quality issues. So the water was staying in the system longer than they were expected. We work with them on some other engineering solutions to help on that, but yeah, it's something that just didn't really give much thought to as far as all this is.
Mm-hmm. Mm-hmm. Yeah.
Our last talk for the session.
Thank you. Hi, everyone. It's a pleasure to be here. My name is Adriana Zuniga-Teran. I work as an assistant research scientist at the School of Landscape Architecture and Planning, and also at the Udall Center for Studies in Public Policy. Today, I speak on behalf of Professor Christopher Scott. He's the director of the Udall Center, so my boss, at the Udall Center, and he was part of the team of Net Zero Urban Water with Courtney and Dom and Tom and others. And he was going to speak about the public policy component, the human aspect of this idea of net zero urban water. And that's what we do at the Udall Center. We work on public policy and mostly related to water. So I will be presenting the work of my team at the Udall Center, including Andrea Gerlach, Stephanie Buchler, and a little bit of my work as well. So the public policy component, the human aspect of this model, we see it in two particular aspects. First, of urban water security and resilience. We work on several projects that look at that in terms of water supply adequacy, water reuse, equity. I'm a big proponent of equity. I look at environmental justice in access to water, its governance, programs that have been developed to address these issues, and the outcomes of those programs, whether they worked or didn't work. We look at broader sustainability goals, and of course, we emphasize the need to be flexible and adaptable to incorporate uncertainty into the decision making and the policy making aspect. We also look at the need for mechanisms to engage people, policymakers, and the community at large. So we look at policy outreach, or reaching out to the community to have their input in policy making, to make inclusive processes, but also we look at policy enrich. So studying at those policies and looking at whether they worked or didn't work the way they intended to work. So we partner with the local government at different levels, the city, the ward, the county, and of course with the civil society in all the ways they can be organized. The best would be neighborhood association and NGOs that are already, they have system in place and channels of communication with the government. So in terms of engagement sites and mechanisms, I'll touch on mechanisms. We see engagement basically at two levels. On the ground, with community, with people, regular people, and also between organizations, between civil society organizations, that would be stakeholder engagement and so on. I'm here showing you two examples, one of each. On the left, you can see a couple of pictures of a student green club. That would be on-the-ground engagement effort. It's seed funding from CAPLA. They gave us a little pot of money to hire students, and we're testing a mentoring program with youth. So instead of us, the researchers, going to reach out to community members, we hired university students to engage with high school students. So there's a hierarchy that is, there's a grad student, then there's interns, 4 interns, university students, and they created a student club with a high school located in a low-income neighborhood of Tucson to promote rainwater harvesting and green infrastructure. So they play, but they also work, they talk about green infrastructure, and they design a project for their school, and then we implement it along with other organizations in partnership. And on the left, we see a typical workshop with stakeholders where we bring together leaders in the community from other organizations or interested in similar goals like environmental justice around green infrastructure, and see where we overlap, where there are synergies, so we can all work together towards the same goal. In terms of sites, engagement sites, we tried going to the community directly. That would be, the best channel would be neighborhood associations, since they are already organized. Unfortunately, in low-income neighborhoods, there are less neighborhood associations, and those that are listed do not really meet. So those channels of communication with the broader community are sometimes not existent. So we tried instead going through schools and faith organizations to promote green infrastructure and greening, since that side of town, the south side of Tucson, is predominantly Hispanic and low-income neighborhoods are deprived of vegetation. So we are promoting greening there through schools and faith organizations. I'm showing you a few of the projects, greening projects that we have implemented in that side of town. These are at the school, the high school that I talked about before, and this is at the New Hope Nueva Esperanza Church in South Tucson. All of these events, of course, we partner with Watershed Management Group, with the Sonoran Institute, with Tierra y Libertad, with organizations that are working on these topics. So we also look at community values around green infrastructure or green space or parks in this case. I'm working with a colleague, Phil Stoker from CAPLA, to look at how neighborhood design, the way we design neighborhoods affect the use of green space, the frequency in which people visit green space. Here you see a photo of a couple of students surveying residents door to door and ask questions on whether they go to green space, how many times, and so on around the Rillito River Park. Now this is work from my colleague Stephanie Buchler, and she works on projects related to community gardens and an urban farm in Tucson. And she looks at sites where there are sites for urban agriculture, and she's very interested in getting access to healthy food to low-income people. As you know, there are food deserts, mostly in low-income areas. They don't have access to healthy food. So community gardens bring this opportunity of providing healthy food to low-income people. She looks at also at the gender perspective, women organizing themselves, refugee women in particular. It's really interesting. She also studies water use and the sustainability of gardens in terms of, she looked at all the policies and programs and discovered there is a lack of water conservation training for gardeners. They don't even talk about that, which we should. And she looks at the new policy instruments that are put into place by the utility company to reduce the water bill for nonprofits to run the gardens. So that's great, but still there is no attention to saving water. So you see she's identifying some policy gaps through her research that we can improve those programs. In terms of outreach, how do we bring that information back to the community? Well, it's always through stakeholder meetings, the project websites that obviously publish our outputs in terms of policy briefs, research briefs, or handbooks. The big idea here is to translate findings into readable terms or very easy terms for the wider community, very succinct, like a brochure, and also for decision makers who they don't like to read much. So let's keep it short. And then going back to this amazing model that Courtney created, I don't know how she did it, but we're looking at the social system, the shaded areas of this model. We have shaded areas in different colors, but one thing you can notice, it's everywhere. One shade or of another, there is a public policy component, a community engagement need. So the people aspect is everywhere. So a little bit of translating where those social systems are and how do they translate to policy work. For example, the environmental justice and access to alternative water sources. We're looking at green infrastructure, as I mentioned, how do we address those injustices in Tucson to achieve this net zero urban water model that we're talking about. Public acceptance of direct potable reuse. As you know, there is this iconic example where in the 90s when CAP water came to Tucson, they treated it in a newly built treatment plant, and there were quality issues. The public didn't like it. They just would not take Colorado River water. So the people aspect or the refusal to use that water really changed the paradigm. They had to, now instead of doing that, they had to innovate. Actually, it's a big innovation to use that water to recharge the aquifer and then recover it. So we are using groundwater, but the Colorado River is used to recharge the groundwater, and that the public accepts. You see how the public plays a key role on whether those systems and infrastructure get implemented or not. In terms of public environmental values, we look at parks, walkability level that may be conducive of those parks being used or not, and how frequently they are used, what type of transportation system they use, and also community gardens, as I mentioned. And then the public acceptance and adoption of alternative water sources in terms of reclaimed water, whether the public is willing to use that for irrigation of golf courses and so on, or not for drinking water, for example. So going back to this diagram, we look back at where the potential research areas are. These are these squares in yellow dashed lines. So there are potential research areas for everywhere. The public policy here is number one, and you see it's everywhere as well. So some of these potential research areas for the future, in black, I'm highlighting the ones more directly with the work we do in public policy. So it's the public preference and community engagement part that I've been talking about in this talk. That's essential for a future of net zero urban water in our community, whether people support it, what programs there are in place, whether they work or don't work. And also we look at potential impacts of green infrastructure. We identify several research areas that are needed. For example, we have big questions on maintenance. We build all that infrastructure, did screening, and who's gonna maintain that? No one wants to do that. How do we fund that maintenance, and so on? So as you see, the public policy component plays a big role in this idea of net zero urban water. And I like to end my talk with this quote that I think summarizes the main point here. So systems make it possible, but people make it happen or not. I think at the University of Arizona, we are well equipped to address both the systems, the infrastructure, the engineering, all of that, but also the people aspect and making it a reality. That's it. Thank you. I don't know if I can take questions. Maybe not. The biggest policy challenge. Well, the one that comes to mind, Dom, is that there are efforts to address green space, environmental justice issues around green space. The city recognizes that, and they created rebate programs, for example, to help people adopt these systems. But then rebate programs, you need to have money upfront to, apply for that. You pay upfront, and then the city reimburses. And who has money upfront? Well, wealthy people. Again, there's an environmental justice component in that program. So now they are adapting that program, and some nonprofits are lending money to low-income families to apply for those rebates. But then that program also had the flaw that they only look at passive systems, so cisterns and tanks, and not at rain gardens and trees. So we're still having or looking at less greening in low-income neighborhoods. So it's a really iterative process into which we really have to consult the community for their conditions to create programs that are adequate to addressing these bigger questions. So that's the one that comes to mind. The biggest one that I've seen in terms of green infrastructure is the maintenance. It's a hot potato. No one really wants to take care of it forever. If the Tucson Department of Transportation is doing those streets like Courtney mentioned, who's gonna maintain it? They don't really like that. If you put asphalt, they are done and they walk away. But if you put trees, you need to go back and trim them and clean them and water them. And that's a big push. People, and anyway, maintenance is for me the biggest question in greening. Thank you. Great.
All right, well, I just want to thank everybody for coming to this session and thank all our speakers, if you don't mind. I hope that the idea of the talk, while it was more on we did keep it more on the water theme, the idea was trying to show, large scale challenge, the need for integrated solutions, innovative technical solutions. You've got planning, policy, social aspects, right? Joel put up very nice the layers of the food, energy, water. You could look at energy and kind of draw this similar kind of diagram and come into similar challenges. So one of the things we've been trying to do in this portion of building a changing world is to get faculty together, to look at these large challenges, and hopefully bring people together with the expertise to solve these in an integrated fashion. So if you're interested, keep coming to these events. We'll be having, hopefully having more of these over the upcoming years. And, you know, but just to, again, just hopefully this gives you an idea of the scale of things that you can do, right? There's very detailed, there's very individual things that can be done in this big picture. There's integrated aspects that can tie all this together. And it can range from, like, again, from the technical to the policy side of things. So hopefully, you know, we've shown that to you and it'll help maybe inspire you. And thanks again for coming. And we do have the keynote, I think, starting at 3 o'clock, our final keynote. So thank you very much.